just for you guys that don't know me, my name's Brian Mann. I've been in an industry since 1996, turning a wrench, and I've been, in doing that type of stuff for well, you guys do the math, you know how long. But I started a mobile diagnostics and programming business back in 2011. That's when I learned so much about the need for basic electrical understanding and testing in our classes, or I mean, in our shops, and the need for it in classes and for our technicians. So it was about 20 years ago that even though I had already been to a trade school and I've been to all kinds of training, but I wasn't applying it. Okay. I got 20 years ago, I got my tail handed to me by a simple situation, and I was testing things wrong. And that's all there was to it. All the information other people tried to pour into me, I wasn't applying it, or I wasn't understanding in a way that would make me help vehicles get fixed. I was open circuit testing or unplugging things and testing it unloaded, which just leads us into nothing but mischief and problems. So being that I had that mobile diagnostic business and I got out of that, I started teaching. I want to train people on how to better diagnose. And everything I've been doing has been hands-on. I got all kinds of demonstration boards such as this, which looks like a spaghetti mess, but I like to teach with real world scenarios and situations. And this is another one. It's real switches and real fuse box. All the wires match and we can bug it. I like doing this type of teaching because I feel it helps technicians apply it directly in class. But as with we know with the new way things are right now, online is the way to go. This is an example right here that you see. This board here is a something we will probably be trying to do live towards the end of the class. I've got a couple demonstrations, which it's a simple circuit, and that's basically what we're going to be going over here. So I want to talk about the agenda for this afternoon, for this hour that we're going to spend together. I want to quickly talk about the increasing technology and on the cars, and then we're going to talk about basic electricity, basic DC circuit refresher. I want to make sure that you guys understand the basics. And we're going to talk mostly about series circuits, a little bit about parallel. We have mock-ups that I put together, and if you guys are more advanced and you know this stuff, as we go, you're going to have the opportunity to tell me what the answer is. Tell yourself. You don't have to chime in. We got a lot of people here right now. So we got over 85 people or 83 people attending. So it's almost a challenge to yourself to make sure you're sharp. If you know this stuff, let's see if you can come up with the answer and be honest with yourself. And then we'll go through it together. And the people that are still learning and struggling or trying to improve themselves, we'll give the answer and I'll try and explain it as we go. So that's kind of how we're going to be going through here. If you have questions, I will try to answer them. I see a hand raised, and I will try to answer. We'll have more or less an open question and answer, but it's going to be just about impossible for me to keep up with 83 people as we have right now. So also, as the class goes on, we're going to do a multimeter refresher and live voltage drop demonstration is my goal, and we may have enough time to go on from there. So I'm going to lower all the hands, and maybe down the road as there'll be points, I'll ask questions and I'll try and take a few questions, but it's going to be very difficult for me to keep up with everybody. So that's what we got going on here. And we're going to try and, like I said, do the open question and answer. This line graph is my own. Okay. It's not from anybody. This line graph is about the technology in cars, whether we're talking about modules and computing power or a combination of both. This is how I see it, guys. And right now we're at 2020. We're right here. We're on the upward curve of this. However, most of the cars that are coming into your shops are over here. Right now, most of the cars that are in your shop, oh, you can't see me. Aspect ratio is off. Is anybody else having that problem where they can't see? I'm not trying to have you see me. I want you to see the demonstration I'm doing. Is anybody else having that problem? Raise your hand if you're having a big problem. It should be working. I've done this quite a few meetings here. So, okay, you're good. Sweet. Well, if it's a problem for everybody else, we'll address that. But what I'm getting at here is technology is increasing, and our knowledge and understanding of basic electricity is so important to be able to see and know about. So why do so many technicians struggle understanding electrical testing? I really feel personally it's because electricity has a few components. It has many components, I guess you could say. It's hard to see, and it makes it hard to visualize. there's a lack of understanding sometimes of basic terminology, maybe a fear of hybrid voltage, or, you know, there's all kinds of things. But I guess what we're going to be getting at is that we have to trust our gauges, our instruments that we're using, which would be our multimeters and stuff like that. So as we go through here, I want to make sure that you guys understand or think about something real quick. You guys think about a 1.5 volt battery. That's what, you know, you're not worried about that. That doesn't scare you. You're not concerned about voltage. Somebody else is saying they can't see me. All I see is a dark screen. Is anybody else having that problem? That's popped up on a chat. If a bunch of people are having that problem, I'll see if I can investigate. But my screen is working okay, and I got to test one over here, and I can see it. So a lot of people are saying they're good. So I'm not okay. You see me in a battery, perfect. Thank you. All right. So a 1.5 volt battery. Just think about that. Think about a 12 volt battery. You guys deal with this every day. Okay, every day in your adventures, we are dealing with 12 volt batteries. But when you think about stuff, people are a little more hesitant, or they think a little more when they think about household electricity, or other people across the pond may call it mains power. When we talk about that, you know, it'll hurt if you touch it wrong. And if we talk about this type of stuff, high voltage electricity, it's kind of scary. You know, you got to watch out for that. So I want you to be thinking about different things that we just shown, these different voltage levels and different batteries and such as we go through. So I got a hard question. What is electricity? All right. If we go to Wikipedia, they basically say it's lightning, static charge, electrical heating are ways we see electricity. But right here, they talk about the movement of electric charges and is an electric current, and it also produces a magnetic field. Guys, this is really what we're talking about here, the movement of electrical charges. If you Google search it, we get a form of energy resulting from charged particles such as electrons and protons, and we're going to be talking about electron charge. And when it moves, it's dynamically as current, okay? So that's what basically a lot of our testing on automotive is, talking about the dynamically moving charges, which is current, all right? So anytime we're going through this seminar here, if you see this red box, it means I think it's really important. I'll probably repeat it 5 times in one way, shape, or form. So keep that in mind. Simply put, electricity is the movement of electrons, okay? And we're going to hit more on this in just a second, all right? So don't forget about that. And I got another question for you. Does amperage kill? I'm sure a lot of you have heard the term, it's not the voltage, it's the amperage or whatever. Well, think about this really hard. Does amperage kill? And we're going to go ahead and get back to that in a little bit, and I'm going to try and do a better job of explaining it and addressing it. But you guys know, you don't see, what do we see here? Danger, high, what? You fill in the blank. We see high voltage. You know that all day. Danger, keep out. High, it doesn't say amperage, it says voltage. So I want you guys to be thinking about that and relating that back to the sources of voltage or sources of electricity that we talked about earlier in these examples. So we're going to get into the basics of electricity. And I'm not trying to go all physics on you guys and go crazy and make you think too hard, but basically all matter is made of atoms. We know that the more atoms have neutrons and protons in the nucleus, okay? And we have electrons in the outer ring here. And if we have more electrons are negatively charged, a particle is negatively charged. If we have more protons than electrons, it's positively charged. It's very simple stuff. I don't want to go crazy on that. But what I do want you guys to see is that a copper atom has this extra electron out there that's easily moved, okay? So conductors have electrons that are easily moved. Insulators have electrons that are not easily moved. So I want to show you guys this here. And thinking about electrons, all right? This is something I try and teach. I've got this, I got this pipe. This is a pipe, and these golf balls are electrons, all right? And think about this. If I push an electron in, and this pipe is filled with electrons, I push one in, one comes out. If I push one in, one comes out all day long. That's what happens. So I want you guys to just think about that. Your copper wire, it already has electrons in it. There's already electrons there. Our battery is creating a difference in potential, and that difference of potential allows those electrons to flow. So I want you guys to really try and grasp that. And it's such an important concept to understand that when we're talking about current flowing. We're talking about electrons flowing. All right. And going to the next screen here, once again, simply put, electricity is the movement of electrons. And in this example of a direct current, you're seeing these atoms of copper or whatever it is here. I don't really care what it is, but we're just needing to understand that we're having electrons move because of difference in potential. And that difference of potential is what we're talking about. So what do you have to make something move? We have to have a push or a pull. We have to apply pressure or force. And when there's a difference in force or pressure, an object will move. All right. So it's important that you guys understand that when there's a difference in force, the object will move. In our case, we're talking about electrons. When there's a difference in charge or electrons, the current will flow. And voltage is the pressure that causes current flow. Guys, you have to be sure to remember this. This is super important stuff. If you can start wrapping your head around this and think about it this way, it's going to be easier for you to diagnose circuits. So once again, if I highlight it, it means I think it's really important. All right. So I have a couple raised hands here. Let me see if I can possibly hop into chat and see if there's something I can answer. Looks like M&Ms to me. Yep. Where do I find a password to join on PC? That should be in the link that they sent back to you. If you check your email where you registered, that'll be there. So I'm going to go ahead and continue on here. So basic DC electricity. All right. There's some common things that we have to understand here. And amps is equal to current, and current is electrons flowing. I want you guys to understand that. It's very important that you guys get a grip on this. Volts is the electrical pressure, the push of the electrons. Without volts, we don't have any electrons flowing. We will still have electrons in our conductor. We didn't change the atomic structure of things. We just don't have them flowing. And ohms is equal to resistance. Resistance is the resistance to electrons flowing. It does what it says. It's really important that we just keep things as simple as we can when we talk about these things. So if you want to get scientific, 1 amp is equal to 6 quintillion, 241 quadrillion, 509 trillion, 300 billion electrons per second. You don't need to know that. I don't want you to even try to remember that. You just have to understand when we talk about amps, we are talking about actual real electrons flowing, whether they're flowing through this pipe like we were showing before, you know, they're popping through here. We push on, if I push on one on this side, it pushes on the one on the other side, okay? You got to understand that. It's super duper important. So that's what we're talking about when we're going. Now, when we're talking about a series circuit, and in my opinion, almost any circuit that we work on a motor vehicle is usually able to be broken down into a simple series circuit in one way, shape, or form or another. All points of current, all the current in the whole circuit is the same everywhere. It's the same in the beginning. It's the same in the end. So I want to show you guys this. This is not, I'm not being too overly scientific here, but I got to make sure you guys get this, okay? This pipe, imagine this pipe is your, this is your starter wire, the wire from your starter motor. These electrons are already in the pipe, but I'm just going to show you if I drop one in, oops, drop one in, one comes out all day long. So you guys got to understand, this is basics of a series circuit. If I drop three electrons in, 3 electrons come out the bottom. You have to get that through your head. It's going to make your life easier as a technician if you can understand this. It's so important to get a grasp on this. So when we're talking about this and talking about the current flow at any point in a series circuit is the same. And I'm going to show you that in just a second. So, but we're going to talk about voltage. Guys, voltage is the electrical pressure within a circuit. It is so important to understand this. This pressure is caused by an imbalance or difference in potential or electrons. If you have no pressure, nothing will happen. No current flow will happen. Guys, think about a dead battery on a car, or if you're talking about a battery for a flashlight, I don't care what it is. What that dead battery is we don't have a difference in potential or a difference in electrical charge from one end of that battery to the other, okay? And when we have that no difference, we do not have any change in our current. We have no current flow. So that being said, I want to make sure you guys think about resistance. And resistance does what it says. Remember this. Resistance resists the flow of electrons. Resistance, of course, is measured in ohms, and I said it does what it says. As current flow is restricted, voltage will be dropped across the resistance. This is so important. When I say voltage dropped across the resistance in a series circuit, we want our load to be where the voltage is dropped, okay? And we're going to get into examples, and I'm going to show you that. So here's an example of a resistance, okay? I want you guys to take a look at this. And we had our starter wire before. We had our starter. Whoop, nothing like being live. We have our starter wire or a heavy gauge wire, and this is our conductor, and we push one electron in, and one electron comes out the bottom, right? Very easy. And guys, if we don't have any resistance, we have no change in pressure in this pipe. I think all of you guys have heard of water analogies, and we've talked about stuff like that before. Well, here's that same diameter starter wire. And if I go ahead and grab some of my electrons and I drop them in the top, they're slowed down. Did you see how long it took for them to come out? Sometimes they'll actually get stuck in there. And this resistance is slowing down, or I should say restricting the flow of electrons. It's so important to understand that when you have a green wire on a car or resistance, this is what's happening. We're bottlenecking this, so we have a difference in pressure. If we push real hard with all those golf balls here, they aren't going to squeeze through. They get jammed up in here, okay? And that's going to cause higher pressure on this side than this side, all right? So it's really important that we try to get a grasp on that and understand it. I see a question in chat. Think of the term and concept potential is poorly understood. I agree with Eric. Yep, the water analogy helps out a lot. For sure it does, no doubt. So guys, I don't want to go into too much mathematics and Ohm's law, because I'll be the first one to tell you, I don't use a calculator when I'm fixing a car. I really don't, but we have to understand the concept. And basic electricity of Ohm's law is voltage divided by amps equals your ohms, or voltage divided by your ohms equals your amps. Basically, if you cover up any one of these parts of the equation, if you cover up any one of these parts here, if we were to cover up this, voltage divided by ohms equals amps. And then if we cover up our voltage, amps times the ohms equals your volts. It's a relationship. It's a law. When I say law, I got to be careful. I'm not going to be trying to be too scientific, because this applies to ohmic materials. And what we're dealing with on the automobiles are, generally speaking, ohmic materials, okay? All the stuff we deal with follows these laws as far as I'm concerned, okay? So once again, 12 volts, and we have 3 ohms, that equals 4 amps. We have 4 amps flowing through this circuit, all right? Very easy to see. I want to make sure one other thing that you guys think about is power, okay? When we talk about power, power is measured in watts, all right? You guys have, if you know, your volts times your amps equals your watts. That's just a law. We're going to try and cover just a little bit of that, because I think it's important for you guys to understand that, you guys know when you buy a light bulb for your home, excuse my dog, he's having a problem over there. If you buy a light bulb for your home and it's 60 watts, well, you're expecting 60 watts of work or power out of that light bulb, and that's what you're getting. So just keep that in mind. Power is the work that we expect a load to do. It doesn't change. It's just the way it goes. So I want to make sure you guys think about that. And in this example, if we have 4 amps and 12 volts, 4 amps in our circuit, and 12 volts is being dropped across our load, we can take our 12 times our 4 and get 48 watts. That's basically how it goes. So once again, just going over this equation, we don't have to be doing math all the time, okay? I just want you to know, if we take this 12 volts and we have 3 ohms, we get 4 amps. But watch this. What happens if we increase this 3 ohms? If we increase our resistance, what's going to happen to our current flow? It's going to go down, okay? So one of the key rules here, and this is what you have to understand when we're diagnosing, fixing, and working with electricity on vehicles, or probably just about anything, this applies to a lot. If the source voltage, which is our battery, stays the same, and the resistance of the circuit goes up, our amperage goes down. Now, when we talk about a light bulb or a heater element or whatever, I'm just using general examples, but generally speaking, the resistance of our load isn't going to change in most cases. in most cases, the resistance of the load stays the same. It doesn't go up or down. It might change because of thermal things, and we're not getting into that scientific of an aspect of it, but I got to make sure you guys understand our load, our light bulb resistance or resistor doesn't change, okay? That stays the same, but if we add more resistance to the circuit when we get our green wire, our corroded wire, or ultimate resistance, an open circuit, our amperage goes down. That's what you have to have a good grasp of. It's so important. So make sure you guys understand that. We're going to go ahead and move into the section of this class, should I say, that's kind of using circuit drawings. And I'm going to have meters on here. Please do work with yourself and try and answer these questions to your best of your knowledge. I want to make sure that you know, even if you know this stuff, you should be able to answer it really fast. If you don't know it, you know, it's going to take a little time, and I'll walk through it quickly with you. In this example, we're using a 12-volt battery. Excuse me. We're using a 12-volt battery, and our light bulb over here is a 6 ohm load. That means we have 2 amps of current flowing through the circuit, okay? What did I tell you about series circuits? The amperage is the same. And just for those of you that aren't familiar with diagrams, this basically, this is a ground symbol and this is a ground symbol, and we could just imagine that these 2 wires are attached together. That's how we should be thinking about this. So if I have 2 amps of current flowing through this point of this circuit, how much do you think is flowing through the point down here, or the point down here, or down here, or over here? If it's a simple circuit like this, the amperage is the same everywhere across it. How could I possibly push one electron in and not have another one come out when I have these things stacked up? It's so important that we get a grasp of this, that whatever is going in is coming back out as far as electrons. All right, no matter where we test this circuit, this series circuit, the amperage is the same at all points across it. All right, we're going to continue on with this circuit. And those of you that are very familiar with this stuff, we have a multimeter here, and we're connected directly to the battery. Maybe I missed it there, but it's pretty close. What should we see? If this is a, let's just say this is a 12-volt battery to keep things simple. Okay, we're going to keep it as simple as we can. We're going to have 12 volts. Okay, the meter is our pressure gauge. It's measuring the pressure between the positive and the negative, and we're seeing 12 volts. Now, if we move down further, and this load is on, the circuit is good. We are not taking into account the regular voltage drop, the minute voltage drop that will happen in any circuit at this time. I'm trying to keep this as simple as we can. If I go from battery negative to the load, and the load is plugged in and the circuit is working properly, what do you guys think we should read there? I think most of you already know, and we're reading 12 volts. And the reason we're reading 12 volts is we're on the same piece of wire. We should read 12 volts. In reality, we might read 1 or 2 tenths of a volt less, maybe 3 tenths, depending on how big the circuit is. But I just want you to get the feeling that this is the same piece of wire. Okay, for when I go here to here, this is the same circuit. We should not have any change in that voltage on that same circuit. The voltage should be the same across that circuit. Okay, and if we go across our load, what you guys, I'm just going to go in slow to make sure everybody has a chance to look at this and think for themselves. If we go across the load, and I'm telling you, in a series circuit such as this, the load is supposed to be the main resistance, and that is the resistance in the circuit. And the resistance, anytime current flows through resistance, we have a voltage drop across that load. We should be dropping really close to our source voltage across that light bulb, and that's what we do. So I want to make sure you guys are understanding these basic concepts. Now, this is where I lose a lot of people right here. This is where people tend, if you're not familiar with this, they get confused. So here we are on our battery negative, and we got our positive lead over here on the ground. Well, think about this. We should be, in theory, on the same circuit, so we expect very low voltage. This is a voltage drop across the ground. It's not very hard, but you know, if we saw 1 or 2 tenths of a volt, like 0.1 or 0.2 volts, that's okay. We're going to see that. And it's very important that you start using your meter, if you aren't, to do voltage drop testing in circuits. And you'll learn real quick what normal is, okay? So once again, I'm showing you here, we have 12 volts dropping across our load, and we have 2 amps, okay? We have 2 amps of current flowing through that load, and we have 12 volts being dropped across it. Volts times your amps equals your watts. So when your customer is using their power, whatever, if we said this was some sort of motor, they expect a 24 watt of work to be done right now. And that's what your customer expects. I want you to understand that as we go through here, the 12 times a 2 equals 24. Okay, so you got 24 watts. Let's go ahead and, we've got a problem. Let's pretend this car comes in and this load is not doing what the customer expects it to do. All right, so we test at the battery, we test our battery, it's good. We test at our load and we have 9 volts. Well, that load was designed to work on 12 volts. Well, we can get it mathematically about what's going on. But if I put an amp clamp on there, I only have 1.5 amps of current going through. And you may be saying, well, hey, Brian, big deal. We had 2 amps of current before. Now it's only at 1.5. I don't understand what the big deal is. Well, what you got to understand, and this is where a lot of guys realize or mess this up, is before we had 24 watts of power happening. Even though we only went down 3 volts in our voltage across our load, and our amperage only went down half an amp, so we're still at 75% of our amperage. You got to remember that the power, the work that's completed by this circuit is a function of the voltage times amp. So when we lose both, well, this is what we get. We get 13.5 watts. We have a significant decrease in the work that's taking place on this vehicle. So I want to take a look at why you don't want to open circuit voltage test. Do you see how, if I go back here, this circuit is live. I have it turned on. We're back probing per se at the test points there. So we're trying to load a circuit. We're trying to use it. Do you guys see what we have here? We have 9 volts. Let me ask you, what's going to happen if we unplug that light bulb and test for the voltage there? Those of you that are experienced, I'm sure you already have the answer, okay? And there's a lot of chats going on. I'm having trouble keeping up. And I don't mean to not talk to you guys, but I will try to do it. I'm a one-man show here. So I want to make sure you guys understand, with this thing unplugged, we get 12 volts. And we'll be thinking, hey, well, I have my source voltage. And this is open circuit testing. This is not the way to test vehicles, guys. You have to make sure the circuit's plugged in and it's on, and we're trying to load it. All right. So the way to test this here is if I was dropping 9 volts right here, I want you guys to see this, and I move my multimeter lead up to this point. If I'm here and I have 9 volts and I move over here, and this is our bad spot of our wire, this is our green goblin going on. If I move it over here, what do you guys think I would see? Before, when the multimeter lead was right there, I had 9 volts. What do you think we're going to have right here? Well, we should have 9 volts. That's what we would show. And if we move our multimeter lead to this side, if our source voltage is 12 volts and I'm dropping 9 volts across my bulb, how much voltage do you think we would show right here? Well, we're going to show 12 volts, okay? I was tricking you a little bit, but I want you to see, we see our source voltage. So we know between here and here, we have our problem. And we're moving our multimeter leads down the circuit until we find the restriction. We found the restriction going on in our circuit right here. Our multimeter is a pressure gauge. Think about it like that. And we have 3 volts of pressure being lost across this resistance of 2 ohms. So I just want you guys to think about this type of thing and how that applies. So that's just one way. I want to touch real quick on parallel circuits. And basically in this example, just so you know, we have a 12 volt battery just like we did before. We're using a 6 ohm bulb just like we had before. And we have a 4 ohm motor. And I don't want to overcomplicate things. I want you guys to keep stuff simple. But what you got to understand is we still have a source voltage. If we're putting our multimeter here, you guys know what we should have, 12 volts. And if we put our multimeter here, same piece of wire, right? Don't forget this. This is the same piece of wire. We should have 12 volts. If we put our meter lead over here, we should have 12 volts. And if we're measuring the ground, a voltage drop should be very low voltage, you know, 1 or 2 tenths or 0 would be ideal, right? And the same over here. So I want you to understand that what we're looking at is like 2 separate series circuits, okay? They're ran in parallel. But where it gets interesting is to make sure you guys understand we're still dropping 12 volts. The pressure of 12 volts is still being dropped across this motor. And we also have pressure of, what do you think, guys? 12 volts being dropped across this light bulb load. So it's important to understand this. Now, what about the current? We have a 4 ohm motor with 12 volts. So we have 3 amps that are going to go through either side of this motor. So we have 3 amps coming out down the bottom That means we got 3 amps going in up here on this branch of the parallel circuits. Very important to understand this. For our 6 ohm bulb, just like we had before, we have 2 amps at the bottom here, and we're going to also have 2 amps up the top. Now, I just put this on here so you guys understand that we have 3 amps going in, 3 amps coming out of our motor. We have 2 amps going in and 2 amps coming out of our light bulb. What you got to understand, we have to have on these branch circuits, the feed circuits, 2 amps here plus the 3 amps there is 5 amps coming out of our battery, and the 3 amps plus the 2 amps is 5 amps going back into our battery. I'm not trying to overcomplicate it. I just want you to understand these branches almost like work like branches of water pipes. You could, I love the water analogy. It's always good. It's a great thing. So I want to make sure you guys get a grasp of that. And I want to take a minute. We're halfway through our time together. Does anybody have any questions? I'm going to go ahead and find my chat here if I can get it back. And I have question and answers. Let me see here. Okay, so we have a lot of different things. I am going to do my best to make this webinar recording alive and available to those who signed up. I will try that. And then also let me check our chat here real quick, and we're going to continue, and I'm going to take a sip of water because that's a lot of talking. Give me 1 second. So, and I seem to have lost my chat. I don't know where I put it. Come on now. Was the resistance in the pipe the same as inserting a smaller wire gauge? Yes, Jesse, you could say that. Whatchamacallit, the resistance, if you have a starter motor wire that's very thick, you know, like a 2 gauge or 4 gauge starter wire, and it goes down, that would be considered resistance. I mean, think about it like this. I have more we're going to cover in just a short period of time. But if you have a big fat wire and a little tiny strand that goes to your starter, chances are it's going to heat up and cook really quickly. That's kind of, yeah, that is a resistance, or there will be a voltage drop there because we can't have that amount of electrons flowing through the little tiny wire. I'm going to see if I can get some sort of copy of this together for you guys. And the ground checks, yes, on any circuit, you know, usually you're going to see 1/10 or 2/10 of a volt drop, just about on any circuit, depending on how many amps are flowing. So I'm going to go ahead and continue here. And if you have any other questions, we'll try and get a nice Q&A time going, all right? So back to my question originally, does amperage kill? I want you guys to think real hard about this. Danger, high voltage. Danger, keep out high voltage, okay? And I want you guys to understand and think about something. The voltage is what pushes the current, okay? You're not going to get current flow without voltage. Amperage kills, yes. When you flow current through your body, it will kill you. It takes way less than an amp if it goes through your heart to stop it, or maybe your brain to fry it or something. Super important to think about. Here's an example of my daughter's hand. She's 56.2 thousand ohms, all right? So if we take our battery that we had and just use Ohm's law, and I'm not trying to make you guys do math, I'm doing the math for you. I just want you to think about this. Your human skin is about 56,200 ohms. Once you get into your flesh, and you know, like inside of underneath your skin, where your body's moist and has more moisture content, your resistance is much, much lower there. But I want you to see here, you'd have 26.6 microamps flowing between 1.5 volts and this resistance. So this is not enough amperage to hurt you. You won't feel it, no big deal. Your 12-volt battery that we deal with every day, and you guys lay your arms across there, and you know, probably, you know, if you drop a wrench on top of that thing, it's going to short it out. The wrench will start glowing and you'll cause a fire. You guys get that, but our body has resistance into it. So, you know, we're only flowing like maybe 213 microamps, give or take. That's a rough guesstimate. Talk about household electricity. This is something I want you to think about. The reason we feel this is because we got 2.13 milliamps, okay? We're actually 2,000ths of an amp flowing through you, depending on how you touch it and all that stuff. And I'm not telling you guys to go out and touch this stuff. If you think about, once this breaks your skin and your human body resistance is about 500 ohms, now you got 240 milliamps flowing, 2/10 of an amp. Now you're getting hurt. You could get electrocuted, and that's enough to stop your heart. That's why you don't drop the toaster in the bathtub with you, okay? So When we talk about this type of high voltage, 220,000 volts, you know, it's going to flow 3.9 amps through you immediately. But once it breaks the skin, you know, you got about 440 amps flowing through your body that will vaporize you and hurt you. You know, you're dead. So I just want to talk about that. Think about danger, high voltage. Anytime you're having trouble wrapping your head around electricity, please think about that. You got to have the voltage to push the amperage. Your car battery way back here, you guys know that thing, it'll put out 400 cold cranking amps or whatever. It'll pump amperage. It can flow amperage, but it doesn't have enough voltage to push it through your body. Okay. Make sure you think about that. That's really helped me explain stuff better. And it seems like a lot of my students have enjoyed that, those analogies. So here's what we got to remember as a recap. Pressure makes things happen. Your voltage is your pressure, guys. Do not forget that. Resistance slows things down. If you have high resistance, the electrons still go at the same speed, but the volume of them, they can't all squeeze through the resistance, and it makes the current flow be less than it would be as opposed to without that resistance. If you guys start using these terms interchangeably, voltage equals pressure or potential. If you think about that, I love talking about potential. When I got a 12-volt battery, I have the potential of 12 volts, okay? And just think about that. Or it's the pressure. Think about the pressure. It makes all the difference in the world for your testing. Amps equals your current flow, and ohms is your resistance. So I want to cover a little bit here your multimeter, and I'm going to try and move my camera to get onto a little demonstration, which I'm going to do my best. It's been very hard with lighting and everything else, but we're going to try and make that happen here. Scales and settings can be confusing on your meter, so I'll make sure you cover a few things here. This symbol is for DC volts. This is for AC. Most of the time, on most of the circuits we're working on in an automobile, you're going to be using the DC volt function for testing voltage. Ohms is for, the omega symbol is for ohms, and A is for amps, okay? Just make sure you're familiar with your meter. There are different meters out there that have different scales. You know, if you have a little guy like this, that's a very inexpensive meter, and you have to auto range it yourself, and I can't get that focused. You have to auto range that yourself and make that happen. Let me see if I can stop the share for a second. And yeah, what I was getting at is if you got a small meter like this, you have to auto range it. You have to know kind of where you're going at, what's the result you're trying to read before you start using it. If you have a little bit higher end meter, many of them have auto range functions, but I gotta tell you, if you're using an auto range meter, don't forget to look at what the meter's saying. I've had guys saying, oh, it's got 10 volts or whatever. Well, 10 volts doesn't sound right to me. We're working on 12.6 volt systems. Usually we want to see close to battery voltage. But when we go to look, they're looking at 10 millivolts. So that's no good, or maybe 100 millivolts. They don't understand the scale they're on. So it's so important to make sure you guys take the time to understand your meter, okay? And as I said, many of them are auto ranging. Some meters will also scale for voltage or resistance as well, as you see over here. Get my marker back. This one's on mega ohms. I just want to make sure you guys understand it's auto ranging to mega ohms. Kind of hard to see, but so the scales can be confusing. Just make sure you understand a few things. We can talk about the prefixes and stuff like that. I'm cramming a lot into a short period of time, so I really can't go into it too much, but you make sure you guys understand this. The small m means milli or thousandths. So if we have 20 millivolts, that's 20 thousandths of a volt, which is 0.02. Okay, think about that, 0.02 volts. Kilo is equal to 1,000. So if we have 5.56 thousand volts, that's 5,560 volts. So you got to understand these. And also the big M is for mega or millions. If you have 2.1 mega ohms, that means 2,100,000 ohms. It's just important that you, if you're not familiar with this, start using your meter. You guys can do it. I know you can. There's no question about it. So whenever you're setting your meter on voltage, it's measuring the difference in pressure between the leads. Always remember that, guys. I can't tell you how important it is, and I've said it probably 3 times already. If you're using your multimeter, your meter is measuring the difference between these 2 leads. So keep that in mind. Between here and here, when you set it on voltage, you're measuring the difference in electrical pressure. It makes all the difference in the world for your diagnostic testing, in my opinion. So I want to make sure that you guys understand that part. And Oops. And let's see. Setting the your voltmeter is a pressure sensor. Pardon me, I got a little tripped up there. Your voltmeter is a pressure sensor. Do not forget that. So we want to look for electrical pressure in a circuit. When you're testing voltage on your vehicle, where's the only true ground on a vehicle? I know you guys probably know this, but make sure you're testing at the battery, okay? The battery negative terminal is the lowest point of reference that we want on our vehicle, and that's the best place to ground your meter. There's nothing quite like working on a vehicle, thinking that you have a good ground when you don't, and having skewed readings and start replacing components or diagnosing further down the wrong path. That's very frustrating and it's very annoying. So I just want to make sure you guys know that. If you guys are doing a lot of electrical testing, by all means, please check the battery. Use a battery tester, whether you have an old VAT40 or you have a Midtronics, a digital battery tester. If you have a bad battery on a vehicle, all your readings could be skewed. I don't want to mislead you and make you waste time, but it's a simple test with the technology we have this day and age. There's no reason you shouldn't do that. Also, if you're testing a vehicle, in my theory, in my head, if I'm going to have the key on for more than a minute or two during my testing, I put a maintainer on there. I get a battery maintainer or put a charger on a 2 amp charge or 5 amp, 10 amp, something to maintain battery voltage. Because if you're testing your vehicle and the battery is going dead as you're testing, you will be chasing problems that don't exist, wasting time. That's very frustrating. Also, another thing of my recommendations is to always check fuses with a multimeter. I like to ground my multimeter on a battery. If I have to have a long extension lead, I do that. So I test my fuses with a multimeter. Guys, I own a test light. It's a snap-on one, but it's in my basement. It doesn't leave the house. I don't use a test light. I get people that complain to me about that sometimes, and that's okay. You can do your way, and I'll do mine. But I really feel personally, I like to see what the voltage is there. The benefits of a test light may be that it draws a little bit of current. The defaults, in my opinion, the negatives of a test light far outweigh any of that, in my opinion. So is your test light when a vehicle battery is kind of so-so, what's the difference between 11 volts and 8 volts or 9 volts? You may be able to tell, maybe you won't. I don't know, but just keep that in mind. So, and also testing fuses. I'm sure some of you guys have had a partially burned fuse. This is why I test with my multimeter. There's nothing like having 13 volts or 14 volts on one side of the fuse and 10 volts on the other side. Hey, 10 volts, yeah, we can run most of the stuff on a car, right? What happens to that voltage going across that fuse as the battery voltage, the input to that fuse is dropping down? What's going on? Now systems are going crazy. We're setting U codes across the car. All kinds of nonsense can be happening, all because of a partially burned fuse. So I always recommend that's a way to do that there. So that being said, always check the load plugged in, the circuit loaded, turned on, all that stuff, as we showed you in another example. Talking about amp testing, there's a couple things you should know about. If you have an amp meter, even on a inexpensive little meter like this, it's pretty accurate, believe it or not. It is far more accurate than, say, an amp clamp like this. Now, the amp clamp, I love this. This is quick. It's unintrusive. It has a great amount of things. But talking about your meter and running the current, opening up a circuit and putting your amp meter in series to measure all the current through that circuit, it has a few drawbacks. First of all, you can blow a fuse. I mean, I'm sure you guys have done that. The meter's fused. If you draw more than 10 amps or whatever the scale is, you could just burn up a fuse, and that's no good. Also, you had to disrupt the vehicle. How many times you guys have to recalibrate window motors, sunroofs, reset the clock on radios? I mean, the list goes on. Or the problems you cause. You locked up a radio or there's some calibration, idle learn. You disconnect the battery. A lot of times you cause yourself a lot of work that you don't have to. If you can find a way to get a low amp clamp around the circuit you want to test, you're going to be in better shape, in my opinion. Now, the drawbacks of the current clamp is, just so you know, you guys know it's proportional voltage in relation to the current that goes through it. The pros are it's unintrusive and it's very quick to get a reading. It can be power, ground side, it doesn't matter where you go. But remember, current flow is the same any point in that series circuit. Super important to realize. And also, the drawbacks of the current clamp are the batteries. If the battery's going dead as you're testing, which I've had that happen, you get bad readings. And also the zero, it's not, you can hit zero, but when you move that amp clamp around, you will get different readings depending on the angle that you hold it on. So it's not super accurate. In my case of experience, usually I see anywhere plus or minus 25 milliamps on my amp clamps that I use. And that's good enough to get me in a ballpark for what I'm doing, especially even a low amp draw. Another drawback of these things is they're delicate and fragile, okay? So don't try and snap it closed, it will be damaged. So talking about parasitic draws and amp testing, I'm not going to get into using milliamps across fuses. That's a great way, and that's a whole other discussion in class. Using an amp clamp with a scope gives you guys great insight. I'm not trying to overwhelm you or go outside the course of bounds here, but we're going to see the amperage over time, and that's just, in my opinion, that's a great thing to be able to check out. And as you see here, towards the end, I got down to 11.2 milliamps on my low current clamp. Now you guys understand, I told you I have a variance of plus or minus 25 milliamps in my testing that I've done. So I'm confident that 11.2 milliamps, even if my meter was skewed the wrong way, plus 25 milliamps is well under the 50 or 60 milliamp draw that I expect to have. So I'm confident that my result is going to leave my customer in a good place. So I know we're covering a lot of stuff here, and I'd like to be able to get to some questions. But one thing I gotta tell you, resistance checking is my least favorite mode of checking. I do not like it. I consider this to be a no or no go test. If I resistance check a solenoid or an injector or a primary side of a relay or an ignition coil that I can access, if I can actually get there, if I tested it and it fails, that component's bad. I'm comfortable that that component is bad. If I test that component and it passes, that doesn't mean that that component's going to handle the load properly or it's going to work properly on our load. So just because a component tests a resistance check, in my opinion, the way I do stuff, does not mean that that component is for sure good. So I want you to keep that in mind. I'm not trying to teach you anything new or disrupt your thoughts. But also, resistance checking is not a good way, in my opinion, of testing the integrity of a circuit. I mean, how many times do you see a flow chart? You guys see a flow chart that tells you, hey, go ahead and disconnect this end and this end, and disconnect the computer and disconnect the sensor, measure the resistance on that circuit, and the resistance reads, you know, is it less than 5 ohms? I think they usually say, or less than 2 ohms. And here we are. Here we are. The resistance is within specification, but when we have to load that circuit or current has to flow through that circuit to, say, turn on a purge valve or whatever, it can't handle it, and then we have a problem there. So so it's very important that you guys realize that. So testing the circuit loaded and getting to other advanced testing can come in handy. We're not going all there right now, but I just want to share this, what I think hopefully helps somebody. I want to make sure you guys get something out of that. So as I said, one strain of wire doesn't do it. That's all we need to know. So if you guys can't get anything besides understanding voltage is equal to pressure, okay, don't forget your ohmage is your resistance, or ohms is resistance, and amperage is current flow. Watts is power. Guys, we don't do these calculations. I don't bust out my calculator and fix a vehicle. It's only when I super duper analyze stuff, or if I'm trying to do a case study, that I really try and put stuff together like that. But one thing, if you can't remember anything else, if your resistance goes up, your current flow goes down. That's the very last one here. If your resistance goes up, current flows goes down. This is a fact. This is where 9 times out of 10 the problem is. If you have a circuit problem on a car, it's because of resistance, in my opinion. I live in a rust belt, so I see a lot of green wires. All right, so please remember this. If resistance goes up, current flow goes down. So let me take a second and try and answer a few questions. I do have a demonstration board that is, I guess, live, and I'll stop the share here. This is the actual board we'll work on. Just before I stop the share, I want to know or be able to show you guys, this is our ground. This is a piece of EMT. We'll say that's ground. These 2 wires here are battery positive and our ground coming in right from the battery. And we got a headlamp switch, and right now this board is rigged just like this. I have a resistor in there, so we have a problem. we have a high resistance in our power circuit. I want to go through and show you what voltage drop testing looks like, and you guys can comment. But before we do that, I would like to go ahead and open it up for questions. If you guys want, you should be able to go ahead and if you guys want, we'll work through this live demonstration, and I'll try to get the lighting right and make sure you guys can see this. So what am I doing here? Give me a second. So, all right, so we're going to go ahead and move the camera. We have right here, we have our voltmeter. We have a circuit that's set up, and the glare there is no good. I keep on experimenting with that. So we have our voltmeter set to volts, and I want you guys to understand that I'm testing at the fuse here, or I can go back and test over here. This is our battery positive. You see we have 12.21 volts. It may be difficult for you to see. I was trying to mess around with this to make it work for people, but I want you to know that I turn my headlight on and I have no power to my head. My headlight's not lighting up at all. So what's the thing that people always do first? They always go and check the fuse usually, and I check my fuse. Here's my fuse. I'm checking one end of my fuse. I got 12.21. I turn the headlight on and off, and I still have 12.2 volts, headlight on or off. I go to the other side of the fuse. This is how I check. Same thing. We don't have any change in our voltage there. So that being said, what's the easiest thing to put in? If this is a headlight, everybody wants to go ahead and put a headlight in it. So somebody replaced a bulb, and of course we have no change in our action of our thing. So I'm back probing the headlight. I know you guys can't really see it, but watch the meter. I have very, very low voltage there. Let me try my other circuit for my headlight. I'm back probing in here. Take a look. I'm going to turn my high beam. I got 2.6 millivolts. Do you guys see that? Or I have 11.7 millivolts. So this is reading in millivolts. It's probably hard for you guys to see. I want to make sure you guys can see that clearly. So I do not have the voltage, our source voltage, dropping across my load. Do you see that? So important that we realize this. So well, the next easiest thing usually to get to is probably maybe pop the headlight switch out of the car. And we have a wire here. The red wire is our input. So you guys can see, look at that. I got 12 volts. Excellent, right? Must be a good input. Well, let's turn the circuit on. I'm going to load the circuit. I'm loading the circuit. What do I got? That went to 7.5 millivolts. All right, so when I turn the switch to off, I'm reading, oh man, that's hard to get. I'm reading 12.2 volts with the switch off. When I flip the switch back on to high beams, yeah, that's high beam. I got 3.6 millivolts. Let me go to low beam. I have 7.5 millivolts. So I would want you guys to see this. If we test the circuit with it not loaded, we get a false reading. So at this point, I know I have a problem that is not at my fuse, because my fuse voltage never changes. I always have 12 volts at my fuse no matter what. So we would start working back down the circuit. And, you know, sometimes it's hard to find, but I want to show you that right here I put this resistor in, as I said. And let's say this is an easy connector to get to underneath the hood. I go to this side of it, and I've got 12 volts, no matter what, 12 volts on this side of it. And this would be, say, inside the connector, and this is the other side of the connector. Say we got a bad connector here. And you can see I have 12 volts when the switch is off. When I turn the switch on, we have millivolts. So what we've done here is we've isolated our voltage drop in this circuit. Now, what I can do is sometimes I like to see it like this. I'm going to take my meter and put it on either side of this voltage drop so you can see that 12 volts is being dropped across here. So right now with the circuit off, let me get that meter so you can see it. With our circuit off, in the off position, I'm reading 0 millivolts. Let me move that so you can see. Sorry about the lighting, guys. I'm having a real difficult time getting the glare down. So we have 0 millivolts. Let me go ahead and turn on, or should I say 0 volts. I'm going to turn the switch to the high beam. And would you guys agree that the majority of my voltage is being dropped across our bad connection right here? This is a resistor. So that's high beams. And here's our low beams. 12.9 volts is being measured between my leads. We have a difference in pressure right here, guys. This is where it's all at. We're dropping pressure. We're losing pressure because of this resistor. If I take the resistor out And I don't know how the lighting's going to work here, but let's get this resistor out of here. Let's make a good circuit again. And I'm going to clip right back onto this connection on one side of the connection and on the other side. And I want you to see what I see here. I have 0 volts. Now, do you guys see how I turn this headlight on? And we have 0.4, 0.3 millivolts. That's low beam. Let's go to high beam. If my theory is right, when we have more current flowing, we're going to have a bigger voltage drop across the same connection. There's a high beam, and we got 0.6 millivolts. So this is real. To make sure you guys understand, this is a real voltage drop across that connector. And I just want to make sure you guys get a load of that. Does anybody have any other questions? I'd be more than happy to try and answer. I love this type of testing. It made a difference in my career when I finally was able to understand voltage drop testing. It made a huge difference in my career, and things took off from there. So Jeff said, unplugging the headlight and measuring can mislead you. Absolutely, Jeff. That's why we do not open circuit voltage test. If you guys seen a YouTube video of me, you want to have a good chuckle. If you haven't seen the video with the same demonstration board you just seen, it's probably about 7 years old or something. It's quite funny. But I thank you guys for attending. If this was useful and you want more like this, let me know. I don't know how much free stuff I can do, but I'm going to try to more practical examples of where calculating wattage is practical and useful. I'm going to have to think about it, Rich, but a lot of times we just have the drop into amperage because of a resistance. We have a resistance go up and we have lower amperage, and that's like all of our problems usually. There can be times when a specific component is faulty and that causes resistance changes internally. So I don't have a great example of that. I usually do the power window example. I like talking about your customer wants to hit the power window switch. They expect power to happen. And if they're expecting, say, I do examples of, they expect, a 60-watt power window motor to push that window up and down. But if they only have 12 watts or 20 watts, maybe the motor doesn't even move at all. So I really do appreciate everybody attending, and I'll try to see if I can put together some sort of handout for y'all, and let me know if you have any questions. If you have questions, you can go ahead and let me see. I got Q&A over here too. I got a chat and Q&A. So, everybody's, a lot of people are asking about the drawings. Can we download drawings? So awesome for beginners, more advanced understanding of electrical diag. Okay, I do not have a recording of the PCM update or calibration lookup class. I'll try to put that together. And I hope this guy maybe makes you think of electricity in a different way. That's what the goal is. You're very welcome. I appreciate everybody who's attended. And there's a lot of stuff going on here. I'm having trouble keeping up.